Okay, this time we're going to have a look at the polarization of light. Now that we've learned about how light is an electromagnetic wave, we're going to see sort of one of the ways we can use this new knowledge to understand some of the behaviors of light. First, I have these filters that I'm going to show you some demonstrations of their use. Now, let's look at what was happening there. First, let's consider here is what a plain electromagnetic wave looks like, right? It has electric fields oscillating up and down like that, and magnetic fields oscillating perpendicular to it. So if I had just one electromagnetic wave and the electric field was oscillating up and down, it would be vertically polarized. We talk about the vertical polarization as the direction that the electric field is pointing in. So this would be vertically polarized light. But when you look at regular light coming, sort of around you, usually it's often unpolarized light. It's a superposition of a bunch of waves where some of it is vertically polarized, some of it is horizontal, and some of it is everything in between. All right, and a short way to represent unpolarized light is to just draw the vertical and the horizontal one and assume that it's all made up of components of vertical and horizontal altogether. And what you saw in that demonstration were these polarizing sheets where you would take unpolarized light, and when it goes through the sheet, it comes out polarized with the light only in one direction. So here's vertically polarized light and here's horizontally polarized light. And when the light comes through, if you think about it, let's say it's completely unpolarized, so all the light there is polarized in random directions. Well, you can see here that you could consider, say, this diagonal one here would be a combination of vertical components and horizontal components. We can break it down into all the horizontal and vertical components. So if you average everything out, about half of the components are vertical and half of the components are horizontal. So if we put a horizontal polarizing filter, let's say, and it only allows the components horizontal through, then about half the light's going to make it through. So if you send unpolarized light through a filter, then you're going to get half the intensity makes it through. So it cuts the intensity in half when you have unpolarized light through a single filter. However, once you send polarized light through it, then what's happening is you're getting a component of the light being picked out. So let's say I send light like polarized like this, all right, and here's the filter like this, then the component of that light pointing in this direction is going to get picked out. And that's going to be a fraction. It's going to depend on the angle here. So you can show Malus's law that if you have polarized light going through a filter, then the light that comes out on the other side is just the intensity of the light times cosine squared of the angle. Okay, so the amount of light that gets transmitted depends on the angle. So I have a few sort of numerical examples of this. So let's say I have unpolarized light I naught here, and it's right here, and it's impinging on a vertical filter. So what's going to come out on the other side? Well, it's going to be vertically polarized light, and because it was unpolarized, the intensity that comes out will be I naught over 2. Simple enough. This second case here, down here, is horizontal. What's the light that's going to come out if I have unpolarized light on a horizontal filter? Well, it'll be horizontally polarized, and because it's unpolarized light, it'll also be I naught over 2. Same with this third one on the top right. What'll come out here, it'll be polarized in that direction, 45 degrees, and the amplitude will be I naught over 2. That's easy. Now, what about when I have multiple filters? Well, let's say I have unpolarized light I naught impinging on this vertical filter. What comes out here? Well, it's going to be vertically polarized. What comes out is I naught over 2. Now, if I put it through a filter that is 45 degrees with respect to the vertical. So the angle between the incoming light and the filter is 45 degrees. So it'll be the intensity that comes, what comes out here is going to be pointing in that direction. And the intensity that comes out will be the original intensity times cosine squared of 45 degrees, which will give me I naught over 4, or 0.25 I naught. So it'll cut the intensity down more. Let's try this case down at the bottom here. So unpolarized light coming through a filter that's 30 degrees with respect to the vertical. Well, what comes out here is going to be making an angle of 30 degrees, of course, and its amplitude will be just cut in half because it's unpolarized light hanging on a filter. Now, what's the angle between this light and this second filter? Well, the angle is 30 degrees. So what comes out on the other side is going to be I naught over 2 times cosine squared of 30 degrees. And when you plug that in, you get about I naught over 8, or 0.125 I naught. See how it works? Let's try just a few more. Well, here, once again, unpolarized light comes out. It comes out at, it's going to be at 45 degrees, right? This is going to be 45 degrees. And so the intensity at this point will be just cut in half. Now, this next one is tricky. What's the angle between the polarized light at 45 degrees and this light here? Well, the angle between them is 15 degrees. There's a 15-degree difference, right? So what's going to come out here is going to be pointing, of course, it's going to be pointing in this angle here, 30 degrees. But the outgoing light is going to be the I naught over 2 times cosine squared of 15 degrees, because the angle is the angle between the incoming light and the filter, and that angle is 15 degrees. And so when I plug that in, I get about 0.467 times I naught, so a little bit less than half. So because the angle is very small between 30 and 45, right, it doesn't reduce the intensity a lot more. This one should be easy, right? Unpolarized light gets cut in half, and it's at 45 degrees. It goes through another filter, so in theory, when this gets cut in half, and when it goes through the other filter, there's no angle, so it doesn't get reduced anymore, so it should still be I naught over 2. Okay, next one I wanted to look at is the interesting, weird example we saw at the end. When unpolarized light goes through a vertical filter, right? It comes out here, and it is vertically polarized, and that will be intensity cut in half. Now, when it goes through this one, nothing comes out, right? Nothing comes out here because the intensity coming out here is going to be I naught over 2 times cosine squared of 90 degrees, which is 0, because there's no component of this light that's pointing in that direction because it's completely perpendicular to it, so nothing will come out on the other side. But if you take the same thing and you add a filter in between them, something weird happens. So that first step still happens, right? We get the I naught over 2 here. I naught over 2. But when it goes through here, suddenly this filter picks out a component of that light that is pointing in this direction, 45 degrees. And so now that will be, when you do the math, it'll end up being I naught over 4. Now that one, oops, this so this should be, sorry, this should not be, let me quickly fix this. This is meant to be the same filters as the other one. So let me just quickly fix that. So it's supposed to be like this. All right, so now that this has a component in that direction, now some of it can make it through here. So now a small section of that will be able to make it through here to the very end, like so. And when you do the math, it'll be I naught over 8. So in the original case, it goes through the vertical filter, and there's no component that can fit through this horizontal filter. But if I had a filter in between, this will pick out a small component of that has a component that can fit through this last one. And it ends up going to I naught not over 4, but over 8. So that's kind of cool. Just for interest's sake here, there's other kinds of polarizations that are very interesting. You can have a polarization that's a superposition of two waves that are out of phase by by 90 degrees. And when you add a superposition 2 waves by 90 degrees and you plot the electric field over time, the electric field actually rotates as it propagates over time. So this is one electric field that is oscillating up and down in the x direction, and one that's operating up and down in the y direction, and then they are a superposition out of phase with each other, and when they add them together, they do like a rotational thing. So with physics experiments sometimes, or certain types of materials do circularly polarized light, and this does come out in certain applications, but I just wanted to show you that mathematically it's possible. The magnitude of the electric field stays constant, but the direction changes over time. So let me show you a couple examples of various sources with different types of weird
She's got a smile that it seems to me reminds me of childhood melodies, where everything was as fresh as bright blue sky. Now and then when I see her face, it takes me away to that special place, and if I stay too long, I'll probably break down and cry. Whoa, whoa, sweet child of mine. Whoa, whoa, sweet love of mine.
GNR, baby.